This video provides a very basic example on material balances. Particularly, we will focus on a commonly used unit operation or process that is called distillation. Distillation is a separation process that exploits the differences in boiling points or relative volatility of components in a mixture. The main goal is to separate the mixture into its individual constituents. This process can be applied to binary systems, such as separation of ethanol from water, as well as for multi-component systems. For example, the separation of gasoline or diesel from crude oil is accomplished through distillation. To illustrate how material balances is applied on distillation of binary systems, let us consider this problem. For this problem, we are given a distillation unit with a feed rate of 5 kilograms per hour, with a composition equal to 8 weight%, or a mass fraction of 0.08 alcohol. Also given to us is a distillate product that is alcohol mass fraction of 0.9, and a bottoms product that contains 3 weight% alcohol. And we are required to solve or to find the mass flow rates of distillate product, D, and bottoms product, B. Just like any problems involving material balances, we will start our solution with the general balance equation, input plus generation is equal to output plus consumption plus accumulation. Then applying the steady state assumption sets accumulation to 0, while the no reaction assumption makes both generation and consumption equal to 0. These assumptions reduces the general balance equation to input equals output, which will be our main working equation for this problem. To begin developing the actual equations, which we will need to solve this problem, let us look again at the diagram that we previously developed, based on the given. From this diagram, we can see that we have one input, F, and two outputs, D and B. By applying our working equation, a total material balance around the unit will yield F equals D plus B. To this equation, we can substitute the value of F, which was given to us, giving 5 equals D plus B. And this is our equation number 1. Now, let us apply our working equation to one of the components of our system, the alcohol. Looking at the diagram again, we can see that we have one input and two outputs of alcohol. The amount of alcohol in each stream can be obtained by multiplying the magnitude of the stream and the mass fraction of alcohol in that stream. Therefore, the alcohol balance around the unit is ZF multiplied by F is equal to YD multiplied by D plus XB multiplied by B. Substituting the values that we know and simplifying, we will get 0.4 equals 0.9 times D plus 0.03 times B. And this gives us our equation number 2. Although we can develop another equation by doing a water balance around the unit, it is not necessary at this point. That is because, if we apply a degree of freedom analysis, that equation will not be independent anymore. This means that, if we add the material balance equations of the two components, we will end up with the total material balance equation, or equation number 1. So, the two equations that we developed are enough to solve this problem. What we have at this point are two equations with two unknowns. We can determine the unknowns either by substitution or elimination. For this problem, let us consider elimination. I will start by multiplying equation 1 by one of the coefficients of the unknowns in equation 2. It doesn't matter which one. Let's use 0.9. Simplifying the resulting equation yields 4.5 equals 0.9 times D plus 0.9 times B. We can now proceed by subtracting equation 1 and equation 2. Notice that the terms containing D's can now be eliminated, and the resulting equation is 4.5 minus 0.4 equals 0.9 times B minus 0.03 times B. By simplifying this equation, we can calculate B, which is equal to 4.71 kilograms per hour. To solve for D, let's substitute the value of B to equation number 1. D is equal to 0.29 kilogram per hour. The calculation procedure that we used in this example can be applied to multi-component systems as well. The main difference would be the number of equations that needs to be solved simultaneously to calculate unknown variables. And, according to the degree of freedom analysis, the number of independent equations that we can develop is equal to the number of components in the system.